people. And I just had taken you through the numbering scheme on cholesterol, which is the standard numbering scheme for steroids. The other part of the nomenclature that you need to know about is because this molecule is fairly flat. It has a top side and a bottom side. And the rings are largely saturated, so they pucker and form what's called a chair formation in most instances. And things sticking above the folded chairs are on the beta side of the molecules, the top. So beta is top. And you can guess that alpha is bottom. So here's alpha and beta. These are two different molecules. Even if the chair conformation were held here, this would still be pointing down. These angular methyl groups, 18 and 19, are above the plane of the rings. And here's that side chain grouping. In the steroids that make up the estrogens, estradiol, estriol, estrone, this ring becomes aromatic. That is, it has 3 double bonds, which essentially mean that the electrons are smeared over that whole ring, and that becomes totally planar, totally flat. So there isn't any boat or chair, it's just flat. And the OH group at position 3 is also in that planar ring, so it's not alpha or beta. If you were to put an OH group out here, however, it becomes beta if it's up. This is estradiol 17 beta. And it would be down if it were the alpha group. Okay, so the ring structures, numbering, alpha and beta, and then this nuance with the aromatization of the A ring. Okay. Steroid synthesis. This is a compilation of all the steroid pathways wherever they occur. Okay. What you need to know about this set of pathways is that not all steps occur in every tissue that makes steroids. In fact, it's usually a subset of the steps that are shown. So for instance, everything down here, from progesterone on down on the left-hand side, is done in the adrenal cortex, but is not done in the gonads, in the male or the female. The steps shown out here, going from cholesterol, pregnenolone, and out this way, these are performed in both the testis and the ovary, but they are particularly anything down here on this right-hand side. None of that occurs in any of the adrenal cortical tissues. This set of steps also occurs in the adrenal cortex, but these out here are only found in the gonads. And the last steps down here are particularly well represented in the female, but not the male. They can occur in the male, but at much less lower intensity or much less common. Notice that the end products that you get on these pathways differ. So if you were in the corpus luteum, this would be the major endpoint. So in the ovary, in the corpus luteum, and in the placenta during pregnancy, the major product is right there. You see little expression of the enzymes that are involved in moving that molecule down these other pathways. In the testis, you're not going to see much of this, but you're going to end up over here. Those are the major androgens, along with dehydroepiandrosterone. Now, DHEA is found in the reticularis zone in the adrenal. But most of the time, you're going to go down in the adrenal cortex down to here, and in the outermost layer down to here. Notice, if we can point this out, notice that these enzymes are the same. These enzymes are the same. These enzymes are the same, and you're going to see that pattern scattered throughout here. You have a lot of redundancy, which means that the enzymes can work on this substrate or this substrate to make this molecule or that molecule. And you see that up further up as well. So there is repetition of the expression of these enzymes throughout. Over here, the molecules over here and over here are all C21. So cholesterol is C17, or carbon 27 carbons. Progestins, progesterone, corticoids, (21 carbons). Androgens, (19 carbons). Estrogens, 18 carbons. So what am I losing as I'm going down this carbon? Okay, you're losing carbon from the molecule. And that carbon loss is usually with the product of what's called a CYP19 gene, or a CYP gene. It's going to be 19 here, 17 is over there, 21A2 is here, 11B1. CYP genes code for a group of proteins that are collectively known as the P450 enzymes. Their function is to introduce oxygens into molecules, and as a result create structures that can be cleaved. Yeah? What was the classic code for you? Okay, so let me get this down. Can I erase that? So CYP genes code for P450, some are 448 proteins, which are equal to enzymes that introduce oxygen, often OH, into carbon structures. Like steroids. They also play an important role in the metabolism of drugs. This introduction of oxygen allows cleavage of carbon-carbon bonds, which is energetically a difficult thing to do. It turns out that these enzymatic steps are irreversible. So when you stick oxygen or an OH group into a molecule, and particularly when you cleave a carbon-carbon double bond, that's an irreversible step. So I cannot go backward from here to here because I've removed the methyl carbon from the C19 position. I cannot go backward from here. Let me make sure I get the right one. 17. Where am I going? Okay. I cannot go backward from pregnenolone, for instance, to cholesterol, because that step is actually supported by the C2022 lyase, which is also a member of this CYP family of genes. So it's an enzyme that introduces introduces oxygen between the long side chain on cholesterol and the 20 position carbon on pregnenolone, which is right here. You notice that's gone when you get to here. So you cleave the bond again with a family member from here. Hydrogen can be moved on or off these molecules using what are called oxoreductases. They're also called hydroxysteroid dehydrogenases. They tend to work in either direction. So I can go from here to here. I can also go back from here to here. Where's another one? I can go from here, testosterone, to androstenedione because there's a 17 beta hydroxysteroid dehydrogenase that puts hydrogen on this bond or across this double bond, so you can go from androstenedione to testosterone. When there was a big brouhaha about steroid use, particularly in Major League Baseball, a lot of the players were claiming that they weren't using drugs or weren't using these steroids because they were, in fact, simply using nutritional supplements that contain androstenedione. They weren't taking testosterone. But you can see why that was biologically irrelevant. Okay, so pathways, but the pathways make sense if you start seeing what links one structure to another. Okay, this is a lot of the same information, but kind of rearranged so it makes it more visible. Here's cholesterol up here with the structural information on it. Here's the side chain cleavage enzyme, which I just mentioned, the C2022 lyase that takes off this chain. Notice that there are two pathways. One's called delta 4 pathway, the other one's called delta 5, that take this molecule and start manipulating the bonds and the OH moieties on it to give you first progesterone in this direction and then down to androstenedione down here or to corticosterone. if you use this set of enzymes. If you go the other way, in fact, if you use the same enzymes but in opposite order, so rather than using this set of enzymes first, if you use them second, you go from here to here. If you use them first, you go from here to DHEA or dehydroepiandrosterone. And then if you use 3-beta-hydroxysteroid dehydrogenase and the 4,5-isomerase here, you go to the same place you would if you used them in the opposite order. This is going on in the gonads. This part is going on in the adrenal cortex. Again, back in the gonads, you can go from androstenedione to either testosterone first and then to the estrogens, or to the estrogens directly. And it depends on the order of application of this aromatase complex, which is also one of these P450 enzymes, or the 17-beta-hydroxysteroid dehydrogenase first. Notice that what you're changing here is this bond to this bond. Everything else stays the same. Over here, you're going from this structure to this structure. Everything else remains the same. And then if you apply the other enzyme, you get finally down to estradiol in the one case, and in fact both cases. This is metabolized further by introduction of an OH group to give you estriol. This is the most common estrogen in pregnancy. Testosterone, when acted on by an enzyme called 5-alpha reductase, which introduces hydrogen across these bonds, gives you dihydrotestosterone. This occurs in the peripheral male structures, particularly during development, and it's important for development. But you can see where the other enzymes occur, are leading. This is showing you the paths specific to the adrenal cortex. So the other one was showing you, where were we? Previous. The other one was concentrating on the Leydig cells in the ovary. Now, let me go back, or let me go to this next one. What might happen if this enzyme were faulty? So it occurs here and here. Doesn't occur here. Where? Oh, here we go. Okay, so you've got this block, and this block. What do you think is going to happen under those circumstances? One person, please. There were multiple answers. Somebody's got an answer. What was it? Okay. So you're not breaking these carbon-carbon bonds here. What do you think physiologically is going to happen under those circumstances?
Well, it looks like you build up a lot of progesterone. You get to progesterone.
Okay.
You couldn't really do much beyond it.
Okay, you get to this point, and you couldn't go beyond it, except where? Here. Okay. And that gets you to these. But you couldn't get the glucocorticoids. Now, what would that mean to the animal? Problems with metabolism of glucose. What would it screw up? Pardon? It would inhibit the immune response. Why? If you don't get the glucocorticoids, would that inhibit the immune response? It would tend to cause it to go out of control. What about the rest of the controls on this system? Okay, what are these steroids doing besides working the periphery? They're feeding back, and what are they feeding back on? What are they feeding back on, folks? What controls the production of these steroids? ACTH, and before that? CRH. Okay? So if I block these enzymes, or this enzyme, and I don't have this being formed, what's going to happen to CRH levels? Go up. What happens to ACTH levels? They go up. And what's going to happen to the amount of progesterone and adrenal androgens that I have present? It's going to go up. Okay? If I've got a deficiency in this enzyme or in this enzyme down here, I can generate a condition called congenital adrenal hyperplasia. Okay? Congenital adrenal hyperplasia. Why hyperplasia? What does that mean?
There's an increase in renewed by one place.
What does hyperplasia mean? Somebody did that for me. Yeah.
Inappropriate growth.
Pardon?
Increasing cells.
Increasing cells, in this case of the adrenal.
Gland.
What part of the adrenal? Not the medulla. Cortex. The cortex. Remember that it's adrenal corticotropic hormone. Okay? It stimulates growth if given frequently enough and in a large enough quantity. And if you got into a condition where it was constantly being stimulated, you're going to stimulate the growth of the adrenal cortex. But what's the problem here?
No enzyme can convert.
Okay, you don't have the enzymes to get to the normal end product. So what do you make?
Progesterone.
You make a lot of the precursors. Okay? Or that part of the pathway that's accessible. And I said it's congenital adrenal hyperplasia. It's going to occur from the time of embryonic development on forward. Any guesses as to what may happen under those circumstances? What if I'm constantly exposing a fetus to androgens?
You're very masculinized.
You're going to get masculinization. And it doesn't matter whether it's an XX or an XY. Many cases of female masculinization are, in fact, congenital adrenal hyperplasia. There was a question over here. Okay. So, synthetic pathways and the consequences of blocking them. Oh, memorize this by Friday. This is here for a different reason. This is the integrated listing of all the enzymes involved in steroid metabolism. Not just in the gonads, but also in those tissues that break them down. And one of the things that this is up here for, and then I think it's the next slide as well, it's just really showing you how you go from a relatively hydrophobic compound like an androgen or even an estrogen to something that you can secrete in the aqueous environment of the kidney. So a lot of the metabolism of these steroids and of drugs or toxins like that share some of the physical chemical characteristics of these compounds is they'll have if you come down these branches, there will be introduction of oxygen species in many of them. Here's a hydroxy, here's an oxono, here's another hydroxy. Over here, there's hydroxy. Sometimes you get addition of something like methyl or acetyl groups on them. But what's happening is the body is making them more and more water soluble. And in order to make them even more water soluble, they'll often conjugate them. This is usually done in the liver. They'll be conjugated to a sugar type compound, like glucuronic acid. So you end up with a glucuronide or sulfuric. The body doesn't use sulfuric acid, but the equivalent is you end up with a sulfate. Here's sulfate or glucuronide. So the body is taking these lipophilic compounds, it's attacking them with enzymes that generate an irreversible step, and ultimately eliminating them by making them so water soluble that they can be filtered by the kidney and eliminated. Okay, this one was androgen, which are C19, and estrogen, C18 steroids. This next slide is the C21 steroid metabolism, starting with cholesterol, and if you follow it down, you'll see the same pattern overall. Okay. One of the things I always hated when I was taking biochemistry in graduate school was the fact that they'd throw up these maps, wonderful maps of all the enzymes present in the pathway, but they wouldn't tell you where things happen, okay? Which made it hard to put things in context. I want to make sure you have some idea of where things are happening. This is a diagram or cartoon of a steroidogenic cell, like you would see in the Leydig cell, in one of the cells of the ovary, or in the adrenal cortex. There's a cell membrane out here, cell membrane out here, obviously extends out here and over here. The cell harvests lipids as parts of lipoprotein complexes, like we went through the other day. In the case of a rat, you'd be using HDL complexes. In the case of humans, tend to be LDL complexes. So there's a receptor. They're usually brought in by receptor-mediated endocytosis, and during their processing through that pathway, cholesterol will be released into the cytoplasm. Now, cholesterol can be used immediately for the production of other steroids. More likely, though, it's going to be stored for a while. And the way it's stored is that it is coupled with free fatty acids. And coupled by means of forming an ester bridge between the 3 position of the OH on cholesterol down on the bottom of that A ring, and the carboxy group on the fatty acid. So you get what's called a cholesterol ester. And this enzyme is something called acylcholesterol, acyltransferase. And so ACAT, I need to draw a picture of what ACAT does. Acyltransferase. ACAT. And what ACAT does is it takes cholesterol, which has an OH on it, and it couples it to a long chain fatty acid. To get a cholesterol ester. So loop out water and you link the two and you've got an ester. Right. So what it's doing is that enzyme is taking cholesterol, packaging it with free fatty acids, and putting it into a cholesterol droplet. Interestingly, this enzyme is reversible. So it can not only store cholesterol, but it can harvest cholesterol. And it does that primarily when it's phosphorylated. Well, when does phosphorylation occur? Well, phosphorylation actually occurs primarily when this system, and this one has been drawn to have ACTH over here, so this would be an adrenal cell. When ACTH binds to receptor, activates the adenylyl cyclase cascade to make cyclic AMP and activate protein kinase A or protein kinase 1. One of the targets is this enzyme. So this enzyme now is primed to reverse this action and give you cholesterol and free fatty acids. Does that make sense? What's ACTH normally stimulating in an adrenal cell? Production of glucocorticoids, steroids. Okay? So, what else is going on? The other thing that's shown here is that cholesterol can also come not only from dietary sources, but from de novo synthesis. And the de novo synthesis starts with acetate, actually acetyl-CoA, which may come from the glucose metabolism. And it goes through a cascade of a series of enzymes. The rate-limiting enzyme in that cascade is one called HMG-CoA reductase. Okay. Anybody drive up from the South Shore along the highway past the gas tanks in the morning? Okay. Where's the slowdown on the highway? Exit 11? Okay, if you're coming up from the south toward UMass, where do you have to put on the brakes or slow down a lot? Pardon? Exit 9? Oh, you must get there late. Kind of the rate limiting step on coming up here on the Southeast Expressway is the merger of Route 3 with I-95, which is just in front of the gas tanks. And that's, but all I was trying to illustrate there is a rate limiting step. It's the enzymatic step with the slowest turnover number. So it's the place where everything has to wait to go through it. Okay. So HMG-CoA reductase is the rate limiting step in this pathway. It also turns out to be a phosphorylation target for protein kinase 1. And when it's phosphorylated, you no longer get cholesterol being able to slow this down. So you get what's called end product feedback on this pathway if it's not operating with a phosphorylated reductase. When it is, it doesn't care whether cholesterol is present or not. Cholesterol is also capable of shutting down the transcription and translation for the receptor for LDL. But again, that is also sensitive to the presence of activated protein kinase 1. So, if you've got a situation where cholesterol is being ignored here, so the cell is actively trying to make cholesterol, actively removing it from storage, and making it available to the enzymes of steroidogenesis. Now, it turns out that the first step in steroidogenesis takes place on the inner membrane of the mitochondria. This is where the C2022 lyase or side chain cleavage enzyme is localized. There is a transport protein called star protein that seems to be a target for kinase. This lyase may also be a target. These two enzymes move cholesterol from the outside of the mitochondria to the inside and allow the formation of that first crucial intermediate, pregnenolone. Pregnenolone diffuses passively out of the mitochondria, and it encounters the other enzymes of steroid metabolism, primarily in the smooth endoplasmic reticulum. That's where you get progesterone being made, the androgens being made, the estrogens being made, most of the glucocorticoids being made. It turns out that the last step between glucocorticoids and aldosterone, which is an 18 beta hydroxylase, is also found in the mitochondria. All these steroids can pass, because of their lipid nature, can passively diffuse out of the cell that makes them. There are no packages of steroids produced like you would get from a protein or a peptide hormone. Okay. You do not need a calcium pulse within the cell like you do for peptides or proteins to get exocytosis to occur. Steroids diffuse out into circulation, and when they get into circulation, they are often bound by specific circulating binding proteins. So there is a logic between how cholesterol is managed within steroid-producing cells and how activation occurs. There's a logic between what proteins are phosphorylated to make this speed up. Okay. We've gone through this one before, so I'm going to skip over it. Not all steroidogenesis occurs in single cells. Sometimes it takes cooperation to get things to work. What's shown here are the thecal cells and the granulosa cells of a developing follicle. The thecal cells sit outside the follicle wall, and the granulosa cells sit inside nearer the oocyte. But when LH acts, it stimulates these various enzymes to give rise to pregnenolone, progesterone, hydroxyprogesterone, androstenedione, and finally testosterone. So the thecal cell produces androgens as a primary product of LH action. This looks a lot like what happens in the Leydig cell in the male. FSH, on the other hand, in cooperation with LH, stimulates the production of progesterone and the production of estrogens. But it can't do it directly. It's missing the enzymes between progesterone and the androgens. As a result, it has to use progesterone, it has to provide progesterone to thecal cells, and it has to utilize the androgen that thecal cells produce, and which diffuses out into the environment, including these next door neighbor granulosa cells, and then it acts using aromatase, which is stimulated by FSH, to cause the formation of this end product steroid. This complex, the major products formed are these, not these. You can see where if you get an imbalance between LH and FSH, or for some other reason you don't stimulate this compartment to grow, what do you get as an end product?
Testosterone.
Okay, well, not just testosterone, but you get androgens, okay? This is what you would see in what's called a polycystic ovary. So you get overproduction of androgens. But the normal operation is this cooperation between the two cell compartments. Multiple cell compartments are also used during pregnancy. So mom is out here. She's this yellowish color. She is separated from the developing fetus by a placenta, which is adherent and integrated into the wall of the uterus. Cholesterol and pregnenolone come from mom's circulation, her diet, anything she makes on her own. And that pregnenolone can be used by the placenta to make progesterone. And it turns out that this is exceedingly active. The amount of progesterone you find in maternal circulation in the later stages of pregnancy is so high you can almost crystallize it directly from blood without much in the way of purification. It's microgram quantities per mil. These C21 steroids get into fetal circulation where they encounter the enzymes that are found in the fetal adrenal cortex. The fetal adrenal cortex is not the same as the adult adrenal cortex. It doesn't operate the same way. It doesn't express the same exact enzyme. It can make cortisol from progesterone. It can make aldosterone from progesterone. It cannot convert the androgens, however, into it cannot take this precursor and route it to cholesterol from what would normally go to androgen production. DHEA sulfate is a C19 molecule. It can be hydroxylated in the fetal liver. Fetal liver is also a different kind of organ. Does anybody know anything about the fetal liver? It's smaller. Nice point. Fetal liver is smaller, but it's the primary erythropoietic organ in the growing fetus. Most blood cell production does not occur in the bone marrow in a fetus. It occurs in the liver. Okay. And so the enzyme metabolism for steroids is also different. You end up producing precursors that can be converted by the placenta again into estriol or into these estrogens, which is why estrogen levels go way, way up during pregnancy as well. The massive levels of steroids, progesterone and estradiol, are part of the reason that pregnant females are so different endocrinologically. Because these control, for instance, the expression of binding proteins in her liver. And those binding proteins include the ones for thyroid hormone, for sex steroids, for a number of other things. But it's a combination of enzymes in placenta, in the fetal adrenal cortex, and the fetal liver that allow the production of these steroids. We've gone over the fact that steroids change on different time scales, sometimes daily, sometimes over decades, sometimes over weeks. Here's a picture of
of levels of hormones changing during the duration of a primate, a human pregnancy. And here you see progesterone going way, way up. The estrogens going way, way up. You'll find out that the placental weight increases all the way, all during pregnancy, and so do the products of it, which include human placental lactogen as well as the steroids. HCG shows a pattern something like this. It's really highest about the end of the first trimester and then comes down somewhat. It's still high throughout pregnancy. This one is just showing testosterone with age in males. Most of the steroids circulate with carrier proteins, so they're bound. Let me show you what I mean. The amount of steroid in circulation that isn't bound with proteins, this is progesterone, testosterone, estradiol, and this is cortisol. The free amount of circulating steroid is only about 1 to 4% of the total circulating steroid. The vast majority of is bound to either specific binding proteins or to proteins like albumin, which are just so abundant that they will in fact bind almost non-specifically to most lipophilic compounds. Notice that cortisol doesn't bind very well to albumin, but it has CBG that ties up most of it. The sex steroids all bind pretty well to albumin. So a picture of this shows you testosterone from the testis, particularly from Leydig cells, binding in various amounts to the binding proteins or free in circulation. The other thing that happens is that this is constantly being drained off and degraded in the liver. Okay. Steroid receptors. Steroid receptors, there are some, a partial sequence is shown for estrogen, glucocorticoid, thyroid beta receptor, progesterone, vitamin D receptor, and retinoic acid receptor. All of those enzymes belong to one large molecular family. And that molecular family shares some features. They all have a three-part structure. There's a transcriptional activation area over here. There's a DNA binding segment in the middle, which is blown up here, and it has what's called zinc fingers. So there's a couple of zinc molecules that are complexed in such a way that they form a three-dimensional structure that has a proclivity for binding to particular sequences of DNA in target genes. The other part of the molecule is involved in hormone binding, dimerization with other receptor molecules, and transcriptional activation. So you've got some activation occurring here, some down here. And they all have a lot of preservation of this structure, this zinc finger structure. Okay. Why don't we pick it up here? We'll finish it off next time. And I will be sending you information on Friday's exam.